Alright, so we're going to start with the review of what isotopes are. Isotopes have the same element, the same mass number, but they have a different number of neutrons. Common example would be uranium-238. Alright, and we're going to review what this means because it's very important. We should know this. Okay. The top number is the mass number, and the mass number is the sum of protons plus neutrons. The bottom number is the atomic number, and it tells you where to find your element on the periodic table. The atomic number is the sum of protons. This big letter, or letters sometimes, is the symbol of the element. In this case, this is carbon. Okay. Target 1. The types of radiations. There are 3 types of radiation: alpha, beta, and gamma. The first one is alpha. The symbol for alpha looks like this. Alphas have the lowest energy, and they don't have good penetrating skills, so they can be stopped by materials like paper, which is pretty weak. Alpha particles are positive, so they are attracted to negative fields. The next type of radiation is beta. The best symbol for beta looks like this. Betas have medium energy, and they have more penetrating abilities than the alpha, but they can be stopped by materials like wood. Beta particles are the opposite of alpha particles, so they are negative and are attracted to positive fields. Gammas are the third type of radiation. These have the most energy and can be damaging. They can penetrate through almost anything. Gamma radiation has no charge, so they are unaffected by fields. There are 3 types of decay. The first decay is alpha decay. Alpha decay occurs when unstable isotopes try to stabilize by emitting an alpha particle. Alpha particles are made up of 2 protons and 2 neutrons. The symbol for this can look like this, or it can look like this. Okay. There are 3 types of beta decay, which is next decay. There are beta emission, positron emission, and electron capture. Today we'll be looking at beta and positron emission. Beta particles are the same thing as electrons, and they look like this. Or they can look like this. A balanced equation for beta emission would look like this. So we are given that the mass number is 14, the atomic number is 6, that makes it the element of carbon. We're trying to find beta emission. Beta emission is 0, negative 1, E. When we combine, 14 minus 0 is 14, 6 minus negative 1 is 7. 7 on the periodic table is the element nitrogen. That's what you get for the equation for beta emission. And positron emission. Positron emissions are positive, so instead of negative 1, it is a positive 1. And for example, we are given mass number 14, the element 7, which is nitrogen. Positron emission is positive, so positive 1 will look like that. You combine, 14 minus 0 is 14, 7 minus 1 is 6. 6 on the periodic table is carbon. That is what that would look like. The third type of decay is gamma decay. Alpha or beta decay produces energy, which is released as gamma rays. Just like this. Gammas have no particles or no mass, so the symbol for gamma decay looks like this. Alright. A quick target 1 review quiz. How many types of beta decay are there? The correct answer is C, 3. What are they? They are beta emission, positron emission, and electron capture. Alright, question number 2. Which decay has the most energy? The correct answer is 2, gamma. Alphas have the least and gammas have the most. Question number 3. Alpha particles are blank, so they are attracted to blank fields. Answer is alpha particles are positive, so they are attracted to negative fields. Correct answer is B. Beta particles, on the other hand, are negative, so they are attracted to positive fields. Just so we know. Okay. Target 2. Writing balanced equations. A balanced nuclear equation obeys the laws of conservation of mass and of charge, which means that the total reactant mass must equal the total product mass, and the total reactant charge must equal the total product charge. Okay, let's do some examples. The first one, write the alpha decay of uranium-238. Okay, so we are given the mass numbers 238. Uranium is a big U, and on the periodic table, uranium is 92. Trying to find the alpha decay, so the symbol for alpha decay is this. You combine 238 minus 4 is 234. 92 minus 2 is 90. When you look on the periodic table, 90 is thorium, and it's written like this. This is the balanced equation for a alpha decay equation. Okay, next one. Write the equation for a beta emission of thorium-234. Okay, we are given 234 is the mass number. Thorium is 90. Alright, and beta emission, so it is a negative 1. You combine 234 minus 0 is 234. 90 minus negative 1 is 91. 91 on the periodic table is Pa, which is protactinium. And this is the balanced chemical equation for beta emission. Number 3. Write the balanced chemical equation for a positron emission of thorium-234. Okay, so we are given that the mass number is 234. Thorium is 90, and it's TH. Positron emission is positive, so instead of negative 1, we put positive 1. We combine 234 minus 0 is 234. 90 minus 1 is 89. 89 on the periodic table is AC, which is actinium. This is the balanced chemical equation for a positron emission. And write the gamma decay of technetium-99M. So we see that there is an M as a subscript. This M means that it is metastable, which means that the nucleus is in an excited state. To solve this problem, we are given 99 as the mass number. Technetium is written as Tc. It is number 43 on the periodic table. Okay, we know that gamma decay has no particles and no mass. So it's written like this. Okay, when you combine 99 minus 0 is 99. 43 minus 0 is 43, which is the exact same thing as technetium, and this is the balanced equation for gamma decay. Alright, target 3, half-life calculations. Every radioisotope has a specific rate of decay. It is measured by its half-life, the amount of time it takes for half of a sample to decay into new elements. Half-lives of isotopes can range from billions of years to fractions of seconds. Uranium-238 has a half-life of about 4.5 billion years. Polonium-214 has a half-life of about 165 microseconds, so it's a huge difference. Okay. You can calculate half-life in 2 ways. The first way being logic. You divide the starting amount by 2 as many times as the number of half-lives. So, for example, you start with 10 grams of a substance. How much is left after 3 half-lives? So our starting amount is 10, and we're going to divide that by 2 3 times because that is the amount of half-lives. Okay, so 10 divided by 2 equals 5. That's 1. 5 divided by 2 equals 2.5. That's 2. 2.5 divided by 2 equals 1.25. That is 3. So we've done it 3 times, which means that there will be 1.25 grams of the substance remaining, and that is our final answer, 1.25 grams. Okay. The second way is by calculating using the formula. The formula is y equals a 1/2 to the x power. Okay, so y stands for the final amount. The a stands for the starting amount. And the x stands for the number of half-lives. So we're going to do the problem we just did, but this time using the formula. Okay, we're trying to find the final amount. Y equals, we are starting with 10 grams, so 10, 1/2, and we're trying to find how much is left after 3 half-lives, so x is 3. You plug this into the calculator and you get the answer of 1.25 grams, which is exactly what we got using logic. This proves you can do it both ways, just do whatever you feel comfortable with. Okay, so let's do some practice problems. Number 1. A certain isotope has a half-life of 6 hours. How much of a 5-gram sample will be left after 24 hours? Okay, I prefer the formula, so let's write down the formula. Y equals a 1/2 x. Trying to find the final amount, and we are starting with 5 grams, 1/2. We're trying to find x. We know that we're trying to find how much will be left after 24 hours, and we know it has a half-life of 6 hours. So we're going to do 24 divided by 6 equals 4. That is the number of half-lives. So we're going to plug this 4 into the x value. We're going to plug this into the calculator, and we are going to get the answer of 0.313 grams. That is how much is left. That is our y. That is our final amount. That's my answer. Okay. Number 2. Carbon-14 has a half-life of 5,730 years. How long will it take for 1 kilogram sample to be reduced to 0.25 grams of carbon-14? Okay, let's start by writing down the formula. Y equals a 1/2 to x. Okay, this one we are given the final amount, which is 0.25, equals the starting amount, which is 1/2, and we are trying to find x. To get x alone, we are going to first divide this entire equation by 1, so we can cancel out the 1's, and we are left with 0.25 equals 1/2 x. To bring this x down, we're going to take the natural log of this function. In order to do that, we are going to do natural log 0.25 equals natural log of 1/2 x, but the x is brought down now, so now it looks right here. To get this x alone, we are going to divide by natural log of 1/2, divide 0.25, natural log of 0.25 by the natural log of 1/2. These cancel out, and you are left with x equals 2. We're not done yet. We know that that equals 2, and we're trying, half-life is 5,730 years. So we have to multiply 5,730 times 2, and when we do that, we get the final answer of 11,460 years. This is how long it will take, and this is our final answer. Okay, our last problem. A certain isotope of uranium has a half-life of 4.3 billion years. How long will it take for a 2.7 gram sample to be reduced to 0.0844? Okay, so we write down the equation. Y equals a 1/2 x. We are once again given the final amount, which is 0.0844. Starting amount is 2.7, 1/2, and we're trying to find the value of the x. We're going to do what we just did to get the x alone. We're going to divide 2.7, and this is going to cancel out, and we're going to be left with 0.03 equals 1/2 to the x. We're trying to get the x alone, so we're going to find the natural function of this. So 0.03 equals the natural function of 1/2. X is brought down. To get the x alone, we're going to divide this by 1/2, and we're going to divide this by 1/2. So these cancel out. You get x alone, and x equals 5.1. We're not done yet. We got to multiply this by the half-life of 4.3 billion years, but to shorten that up, we're going to do 4.3 times 10 to the 9th, which is 4.3 billion years, times the 5.1 we just got. And when we do that, we get the final answer of 2.2 times 10 to the 10th power of years. That is our final answer. Okay. All right. Moving on to target 4, fission versus fusion. When bombarded with neutrons, some isotopes undergo fission. Okay. Rather than alpha or beta decay, they break into 2 smaller atoms called daughter products. Fission can release enormous amounts of energy. It can be controlled in 2 ways in order to allow the energy to be used productively in power plants. The first one being a coolant, like water, and control rods. They are used to manage the speed of the reaction so that it stays continuous but does not get out of control. Neutron moderation. Neutrons slow down in order to increase the speed of reaction. Neutron absorption. Decrease the number of neutrons to prevent reaction from going too fast. These are 2 ways you can control it. Fission results in a, not chain reaction, which we can control with the control rods and coolants. Fusion. Fusion occurs when nuclei combine to form a nucleus of greater mass, which also releases huge amounts of energy. This requires extremely high temperatures to occur. The lighter nuclei combine to form more stable nucleus. They produce less waste. Stars are the birthplace of elements. Through fusion reactions involving hydrogen isotopes, stars produce both energy and all of the heavier elements. Fusion is, we haven't discovered a way to harness or how to capture fusion, so it is quite difficult to understand it. But yes, that's it. That is our nuclear chemistry unit. Alright, and before we go, we have a fission versus fusion review quiz. Question 1. Which produces less waste? The correct answer to that would be fusion. fusion produces less waste. Question 2. Which breaks into two smaller atoms called daughter nuclei? Well, it's not gamma or beta, and fusion is combining, so it must be A, fission, which requires extremely high temperature. It's not a chain reaction. That is what happens with fission. It's not alpha, so it must be fusion. All right, and that's it.